All right, guys, so I just put my kids to bed and I'm making this video. So if you hear chaos ensuing, it's because they're not yet asleep, but we're going to give this a whirl. So we do have some more things to talk about with ionic bonding. So leave some room in your notes because we need to talk about the properties of an ionic solid, like a few specific properties about it, and we also need to talk about Lewis structures, but we can probably talk about Lewis structures when we do covalent Lewis structures, and we can compare and contrast them. So if you're trying to leave a place in your notes, I would leave about 3-4 lines before you start covalent bonding, and then remind me on Friday that we need to cover the properties of ionic solids, because Friday we're going to spend most of the time on Lewis structures, because that's going to take a lot of practice. So covalent bonding, we did ionic, we did lattice structure, we talked about how electrons are transferred. Covalent bonding, that word co means together with. You actually have two nonmetals, usually, okay, and electrons are shared. They're actually shared between atoms. So the orbitals overlap. So your the orbitals we were talking about in chapter 6, right? The electron orbitals, remember my app? They actually physically take up the same space and overlap, and that's what makes it a bond. Where does the bond form is a really, really good question. So I want you to think about potential energy as we sort of talked about it from that Pogel we did. Okay, so let's make this right here 0. I know, that's weird. It's fine. And this is like a positive, and this is a negative, and this right here, this is energy. Okay, and then this axis here is internuclear distance. All right, so what's actually happening here is where, let's make this my 0. Okay, where does your bond form? Okay, where does so internuclear distance, let's first talk about what's on each axis. The internuclear distance is the distance or the space between each nucleus. So if you're thinking about atoms sharing orbitals, and I know that's a Bohr model, okay? You've got to think about these electrons here. This electron is simultaneously attracted to that nucleus and attracted to that nucleus. That's true for both electrons, okay? But the nuclei are being repelled by each other, and the electrons are being repelled by each other. So remember, like charges repel and different opposite charges attract. So what we have here is we have we are trying to kind of balance those forces. We're trying to balance the forces of attraction and balance the forces of repulsion so that they kind of settle into a really nice bond length. Like, where should these two things come? So if these nuclei come too close together, they're going to start to repel. This positive nucleus is going to repel this positive nucleus. And that's where you see this incredible increase of, let me get my highlighter because I have one of those on this, guys. This incredible increase of potential energy. This is coming from your two nuclei repelling because they're too close together. Okay, over here is where they're too far away to have enough attraction. Oh, that's fine. So I'm trying to maximize the attraction and minimize the nuclei repelling, okay? So right here, this right here is what we call your bond energy. That's the amount of energy that's released when the bond forms. And the distance is this distance, okay? This is your bond length. Basically, this is how close together those two nuclei are. The bond energy is like how strong the bond is, okay? So if you have a double bond, it's going to be a lower bond energy. If you have a single bond, we'll talk more about what double and single are, don't worry. But the stronger the bond, the bigger the dip here is, okay? The bigger the dip. All right, covalent bonding. So let's think about a covalent bond. Let's do a different color because I'm getting bored. A covalent bond between a carbon and a hydrogen. Okay, so carbon has 4 valence electrons, and that's kind of a moot point right now. It doesn't matter too much. And hydrogen has 1 valence electron. Okay, and we're going to look at the bond. Oh, this is I don't want to do hydrogen. Let's do fluorine. I don't really want to deal with that guy right now. Okay. Now I'm showing fluorine's electrons as X's and carbon's as dots, just so you can see where they kind of come from. And I'm not going to worry about like what's happening over here, or here, or here. Sure, this fluorine might be over there, or something else might be. I'm focused directly on this bond between carbon and fluorine, if that makes sense. So what I'm looking at here is I want to look at this covalent bond. So you can see that this pair of electrons, so this pair of electrons forms a single covalent bond. So that is going to form a single covalent bond, and the bond length is going to be determined, like we set up here. Oh, wow, that was fun. By, we can move you down, by where we minimize the repulsion of those two nuclei, but maximize the bond energy, right? We want to make the bond as strong as possible and get those nuclei attracting those electrons without getting so close that they repel. All right. So there's my single bond. Now, the electrons are going to spend, they're sharing electrons here, okay? So the electrons are going to spend some time with carbon and some time with fluorine. Now, are they shared evenly? That is the million-dollar question. Okay, how do we know? Well, there's a measure of how strongly the atom pulls on electrons in a chemical bond, and that term is called electronegativity. Now, some of you may have seen this on like practice test materials for chapter 7, because electronegativity follows the same trends as ionization energy. But I didn't want to introduce it there because I didn't want to muddy the waters. I didn't want it to get too messy. I really wanted to talk about electronegativity when we talk about bonding, because that's where it matters. So the official definition of electronegativity is the tendency for an atom to attract a pair of electrons in a chemical bond. Okay, so how strong, okay, is that atom in the tug of war over those electrons, right? So if I'm looking at this, right, I've got fluorine and I've got carbon. Who's pulling harder? Is fluorine trying to pull harder, or is carbon trying to pull harder to pull on those electrons? Okay, so that's what electronegativity is. It follows the same trends as ionization energy. Okay. Boop. Without the exceptions, okay? Which means that it increases across a period and it decreases down a group. And the reasons are the same, okay? It increases across a period because of nuclear charge, and it decreases down a group because of radius or number of shells, okay? So the more electronegative an atom, the harder it pulls on the electrons. Okay, and I'm going to write that down because I think that's pretty important. The more electronegative the harder the pull. Our highest electronegativity is fluorine. And fluorine's electronegativity is 4.0. And our metals are generally low, like sodium I think is like 0.8 or 0.9. Cesium is like 0.7. So our metals are usually very low. Fluorine is our highest. So if we're going to revisit, we're not going to do that. Okay, let's put that there. If we go back up here to revisit our carbon and our fluorine, okay, your Regents reference table has your electronegativity values, but usually you're not going to need electronegativity values. Fluorine has an electronegativity of 4.0, and carbon I think is like 2.6. Okay, so if I'm looking at these two atoms and the bond between these two electrons, there is an uneven distribution of charge here, and that's what we call polarity. So fluorine is pulling with a force of, it's not really a force, but fluorine's pulling with an electronegativity of 4, and carbon's pulling with an electronegativity of 2.6. Fluorine is clearly stronger, so fluorine gets those electrons more often than carbon does. Fluorine gets those electrons more often than carbon does. So essentially, if we're thinking about this pair of electrons, they're going to spend a few times with fluorine and then one with carbon, and then a few times with fluorine and then one with carbon. And so since fluorine gets them more, this bond exhibits, excuse me, as we do this, I gotta go back down. Come on, Buggy. Okay. The bond exhibits what we call polarity. Polarity is the uneven distribution of charge. Okay, remember electrons are negative, so if fluorine has an extra electron for more than half of the time, the fluorine is going to be partially negative. Okay, so if the electrons spend more time with, if fluorine gets this electron more, fluorine becomes partially negative. Now that symbol is a lowercase delta and it means partial. It is not a full-blown negative charge, okay? Because that would mean that carbon transferred or gave its electron to fluorine, which it did not, okay? It most certainly did not. It still has a pull on it, but it's just not, fluorine's not pulling on it enough to pluck it off from carbon. Fluorine's pulling on it a decent amount, so fluorine gets the electron more often, and maybe it only sees carbon on weekends, okay? So carbon essentially becomes partially positive. Okay, it is not a full-on positive, it's a partial positive charge. So we would say that this bond is polar, and we would draw an arrow like this. Okay, the arrow points to the negative one. Okay, the arrow points to the negative one. So basically that shows that fluorine is stronger, more electronegative, so it becomes partially negative in this bond, and carbon becomes partially positive, okay? You can see here that we have polarity, we have an uneven distribution of charge because we have a difference in electronegativity, okay? And so the polarity of a bond comes down to this. Is a bond polar? If your difference in electronegativity between the two elements on either end of the bond is 0, the bond is non-polar. Okay, the bond is non-polar if your electronegativity difference is 0. Give me an example of that, Mrs. Bell. Gladly. Iodine bonded to iodine. This would be like playing tug of war against a clone of yourself. Iodine has the same electronegativity as iodine, so they're going to share that electron perfectly equally, okay? So they're going to share it 50-50. No side is partially positive, no side is partially negative. So this is what we call a non-polar bond. You are almost exclusively going to see a non-polar bond between elements that are the same. Okay, so like H2. All your Hoberfinkels are non-polar bonds. So like H2, F2, N2, O2, etc. All of those guys are non-polar. You would also see a non-polar bond somewhere like this. Like if I had ethane, right there. The carbon-carbon bond is non-polar. Okay, I know this is getting a little bit long. We're almost done, I promise. Okay, there we go. And electronegativity difference. I know I spelled that wrong, forgive me. That's greater than 0, okay, is going to give you a polar bond, which means there's a distribution of charge across the bond, okay? The more electronegative one is the one that's partially negative, and the one that's less electronegative is the one that's partially positive, okay? The last thing we need to know about covalent bonding, okay? We need to know that, let's see. It's a spectrum, okay? The more the bigger the difference in electronegativity, the more polar the bond. That's important. You also need to know that metals with oxidation states or charges greater than, I'm going to say, not greater, but I'd say greater than +3. So greater than or equal to +4 tend to bond with more covalency, okay? It's a spectrum. So the bigger the electronegativity difference, the more polar your bond, the more ionic character your bond has, because ionic is forming fully charged ions. So you've got a positive ion and a negative ion, +1, -1, +2, -2. Whereas we are talking partial here. We're talking like partially positive or partially negative when we're talking about a polar bond, because the electron is not fully transferred from the less electronegative one to the more electronegative one. So we're talking about a spectrum. So the higher the oxidation state on that metal, the more metals, we say metals and nonmetals are ionic, but if your oxidation state is +4 or higher, it tends to be more covalent than it is ionic, okay? So if you're looking for ionic character, you're looking for the biggest difference in electronegativity, or you're looking for a metal with an oxidation state that's greater than +3. So like +4, +7. So for example, like potassium permanganate. Manganese is a metal, but here it's +7. So this polyatomic ion actually has covalent bonds. Okay. We will talk about properties for ionic substances and molecular substances and network substances tomorrow, which is Friday. So we'll talk about it Friday, and then we will start doing Lewis structures, and we're going to spend most of our time on Friday doing Lewis structures and separating them between ionic and covalent, which is important. Okay. I am after school today, if you are watching this in class and not like future years, and I will see you then. Thanks. Bye.